Okay, well, so I left the last video asking you about the type of collision that occurs between this ball and the box. Because the box is initially not moving and the ball moves along and then the two basically become one, this describes an inelastic collision, right? Actually, it's a totally inelastic collision. And in a totally inelastic collision, the change in momentum is conserved from this initial case here, where the box is at rest and the ball is moving, to the final case right where the ball and the box are moving together and they have some mass, right? So there's a conservation, the momentum is conserved in that case, right? So from here to here, delta P is going to be equal to 0 from this top part to the bottom part, okay? The change in momentum is equal to 0. The change in momentum of the center of mass of these two, of this system of stuff, is going to be equal to 0. What isn't going to be conserved between this case and this case, right? In a totally inelastic collision, the kinetic energy is not something that is conserved, right? There's some kinetic energy that's actually lost because this is a totally inelastic collision. Were this an elastic collision, kinetic energy would be conserved. So although we're going to use kinetic energy in this second part to talk about from this point to this point, we're going to use the kinetic energy isn't conserved in this case, but we can talk about the change in kinetic energy by the amount of work done on the ball and the box together. All right? So let's look and see how we're going to put all this together. So we have our change in momentum. So the first portion here, the change in momentum of the center of mass is equal to 0, right? So that means that the final momentum minus the initial momentum is going to be equal to 0. The final momentum of the ball plus the box together, mb plus mx, times the velocity of the ball plus the box. And maybe I should do this bx really, but I'll just do bb like I did before. And that is moving to we'll just count positive x to the right, okay? So this is going to be a positive value. And to kind of be explicit with what I was doing in the other video, we should really call this, some magnitude of the velocity. It won't end up being a problem here, but to be careful, we should make sure that we're always very careful what we're doing, right? This is a positive value because this velocity is moving to the right. So that is going to be subtracted from the initial momentum, which is the mass of the ball times its velocity, okay, plus the mass of the box times its velocity. Minus. And that's going to be equal to 0 because there's no change in momentum during a totally inelastic collision. So the initial momentum of the box, or the initial velocity of the box is equal to 0. And so its initial momentum is 0 as well, right? This is something where the box is at rest. We can then describe the velocity of the ball also is going to the right initially. Right, there he is. The ball is moving to the right as well. So this negative sign comes from the subtraction of the initial momentum, right? Not because it is going in a negative direction. It's going in a positive direction, and a negative and a positive gives you a negative. So if we want to solve for the velocity of the ball plus the box, that would be equal to mb times this quantity vb divided by the sum of these two masses, mb plus mx, right? Just like it was for every other totally inelastic collision we did, right? Should make a lot of sense from there, right? Then, once we have that, I'm going to write that down real quick. The velocity of the ball plus the box is equal to the mass of the ball times the velocity of the ball divided by the mass of the ball plus the mass of the box. Okay? And now we know what the velocity of that ball plus box is. Okay? So we know something now about its, we can describe something about, we wanted to know the initial kinetic energy because we can determine the net work done will be equal to the change in kinetic energy. And so the kinetic energy here is the final kinetic energy minus the initial kinetic energy. Well, the final kinetic energy is 0 because it comes to rest. So 0 joules. The initial kinetic energy is going to be equal to 1/2 times the total mass here, which is mb plus mx, times its velocity, which is the mass of the ball times the velocity of the ball divided by the mass of the ball plus the mass of the box. All of that stuff squared, right? We know what all of these values are. We're given all of these values here in the problem. So this is just a number when we plug this all in. And that's equal to the net work. And the net work is a non-conservative work. And that is simply equal to the frictional force in this case, which is negative, right? Because we know that the frictional force is to the left, right? The frictional force causes a deceleration. It acts against the direction. The frictional force always acts against the direction of motion. The direction of motion is to the right, so the frictional force here will be to the left. So if we wanted to be really precise, this is really the integral of f dot dx, right? Or f dot dr, where dr is only in the x direction, and so this f dot dx lets us know that we're only considering the forces along the direction, that everything's great, and that negative sign comes because the dx goes from somewhere on the left to somewhere further on the right. So positive x we said was to the right, so this displacement is a positive value, and the frictional force is to the left, so they're in opposite directions from one another. So this is going to be times this change in x. Right, so that frictional force that we talked about before is equal to mu k times the normal force, which is mb plus mx times g times the displacement, delta x. And that equals times everything on the top here. Right, so a whole bunch of things will, several things start to cancel out a little bit. We can see that from just kind of looking at it, that there's an mb plus x and an mb plus x here, both multiplied. So if we divide by that, those things will drop out, right? So on the left side, we just get this negative mu k g delta x equal to negative 1/2 mb vb over mb plus mx quantity squared. We're solving for mu k. There's a negative sign on both sides. We can divide by that. We can divide by g delta x, and that cancels on the left side, which tells us that the coefficient of kinetic friction is equal to this whole mess of stuff, which are all numbers that we know. We just plug them in. Life is happy. Okay? Very cool.